First, I want to thank the organizers for inviting me, and also want to thank CRM for hosting this nice conference. I did a postdoc here in 2019. It's certainly nice to revisit this campus and especially this building. So I want to talk about quantum blocks and especially the effect of marking vertices in discrete time quantum blocks. And here's the outline for my proof. First, I'm going to start with the introduction of discrete quantum blocks with and without marking vertices. And then I will define two types of probabilities called the average search probabilities and the average return probabilities. And at the end, I will pose some questions related to these two as well as quantum state transfer. So here's a graph and a matrix that we're going to look at a lot during this talk. This graph has 4 vertices and it has 5 edges. Okay, and it's associated with the 10 by 10 matrix over here. So what are the rows and columns? They correspond to each edge twice. So for every edge, let's say you take the edge 0, 1, you replace this guy by 2 arcs with different directions. So 0, 1 and 1, 0. Okay, because we have 5 edges, the matrix will be 10 by 10. Now, if you look at this matrix, you will see a lot of interesting things. First of all, it's quite sparse. There are a lot of zeros. And the second thing is you can actually describe each column using the degrees only. So let's pick this column, for example. It represents an arc pointing from 1 to 0. So we will call 1 the tail of the arc and 0 the head of the arc. So the column indexed by 1, 0 has only 3 non-zero entries. And because the tail of 1, 0 is 1, the non-zero rows will be the arcs that has the head 1. So you have 0 going into 1, 2 going into 1, and 3 going into 1. Only those entries receive non-zero values. And if the arc is not the opposite of the arc we started with, then it's going to receive 2 over the degree of the tail. So 1 has degree 3. That's why you see 2/3 for 2 going into 1 and 2/3 for 3 going into 1. And if the arc is the opposite of the initial arc, then we get 2 over d minus 1. So in this case, you have 2 over 3 minus 1, which is equal to. Okay, so this rule works for every vertex. If instead I start with a degree 2 vertex 0 over here, then let's say 0, 1. Okay, then for the opposite arc, I have 2 over 2 minus 1, which is 0, so it doesn't contribute to the column. And for the other arc going into 0, I have simply 2 over the degree 2, which is 1. Okay, so that's what the matrix looks like. You can take the inner product of the corresponding columns. You see this matrix is actually orthogonal. So a second observation is U is unitary. The row sum of each row is equal to 1. So U has always vectors the eigenvector. Okay, we're going to need this for future properties. Now, that matrix defines a discrete time quantum block on our graph. So here's the setup. You have a graph. Okay, and you replace every edge by opposite arcs and look at the state space, which is the function sending the arcs of the graph to complex numbers. And how does the quantum block evolve? Well, it's determined by the unitary matrix we described before. It updates your states by multiplying it by U. Okay, and we can specify the action by giving the image of the basis. So if you pick any arc UV, then it's going to be sent to a linear combination of arcs coming into U. And if this arc is opposite to the original arc, you get 2 over degree minus 1. Otherwise, you get the coefficient 2 over degree. That work, all the vertices are treated equally. But in some case, we will pick a special vertex and modify the transition matrix a little bit. And this is especially useful if you have a database and you want to look for a certain data point that satisfies some property, then this is equivalent to finding a marked vertex in a graph. So say I have a special vertex A, then in the evolution, if the arc is not leaving the special vertex, then I keep the same image. Otherwise, I just negate all the entries. So, for example, in this diamond graph, if I mark the 0 vertex, then instead of 1 and 1 over here, I just have -1. That new matrix will still be unitary. And that is one way of marking. Alternatively, I can just send the marked arcs to negative of the opposite arcs. So both those two ways of marking have been studied in the literature. The first one is related to the oracle. So you can describe this as U times an diagonal matrix, which has ones if it corresponds to an unmarked arc and -1 otherwise. So this is like you are asking the computer, right? Am I on a particular arc or not? If the arc is marked, then the oracle tells you yes, which negates the entry, and otherwise it just keeps the same entry. Okay, so that was how the quantum work evolves. And what do we care about the evolution is the probabilities. So let's say I start with an initial state, and usually we will normalize it to a unit vector. Then the probability distribution after t steps is described by this entry-wise product. So because U is unitary, U to the t's times the unit vector is again unitary. So the squared modulus of this long vector sum to 1. So the shear product of this guy with its conjugate will give you a probability distribution. And this is the distribution of all the arcs. Now, this distribution does not converge because a unitary matrix will preserve the distance between two consecutive steps. However, the average probability distribution does converge. So what do I mean by that is you sum up all the probability distributions for the first t steps and then take the average over t. And this will actually converge to a limit as t goes to infinity. So in this talk, I will focus more on this average version than the instantaneous version. Or if I want to know the probability of landing on a particular vertex but not the arc, well, that's simple. You just take all the arcs that starts with this vertex and sum over that. So here's a little animation that shows you how a quantum walk evolves with the corresponding probabilities of the vertices. If you have good eyesight, you can spot when t equals 0, we are starting with the top vertex with full probability. And as t increases, the quantum walk starts propagating, and every vertex will receive some non-zero probabilities. Okay, so part one of my talk is to study the quantum walk where the initial state is every arc. So you start from everywhere, and you want to see if it lands on a particular vertex. And we will only be interested in regular graphs. So suppose the graph is k-regular and it has n vertices, then this always factor will denote the uniform linear combination of all the arcs. And to normalize it, we just divide it by the square root of the number of arcs, which is kn. And suppose the target vertex is A. The question is, how likely is the quantum walk gonna land on this vertex A? So what is the probability that we are here after each step? If no vertex is marked, then recorded U times 1 is equal to 1. This guy is an eigenvector. So at each step, there's equal chance that the worker visits any vertex. So this is 1 over n, and you can see as the graph gets larger, that probability gets smaller and smaller. Now the question is, what if I make the target vertex special? If I mark it, then can I get a non-vanishing probability of finding that vertex? And actually, this is very well studied in the name of a quantum walk-based search. So the first graph people look at is the complete graphs with loops. And in Grover's algorithm, it showed that you can actually make the probability equal to 1. And here are some other graphs that have been studied. And for most of these, there is a speed up in finding the target vertex successfully compared to the classical search algorithm. But there are some exceptions. For example, for these Cartesian power of Cn, when d is less than 5, I think there's not so much speed up compared to the classical case. By the way, both continuous time and discrete time quantum-based search have been studied. But I want to look at not the instantaneous probability, but the average probability, because this one has a nicer expression in terms of the eigenprojections. So we know every eigenvalue of a unitary matrix lies on the unit circle. So I can write it as e to the I theta r for some angle theta. And let Fr be the orthogonal projection onto this eigenspace. Then U can be written as a sum of these times Fr. Now, when you look at the time average probability distribution and take the limit, it turns out you can forget about the sum over the time, and you can even forget about the eigenvalues. The limit completely depends on two things: the initial state, x0, and the eigenprojection of U. So this gives you a very simple algorithm to compute the distribution. Simply calculate Fr and then hit it with the initial state. Take the short product with the conjugate, finally sum over all the eigenvalues. So you can ask the computer to do that for Kn. This is the average distribution for K4. You can see if I mark the first vertex 0, 1, then the corresponding arcs will receive, including this one, will receive a much higher value than the others. And what about the probability of landing on this marked vertex? Then we defined to be this factor of arcs, and then take out the outgoing arcs of the marked vertex, sum this up, and divide it by the normalization factor. So that is called the average search probability. In this example, you will see a probability of somewhere around 1/3, which is not quite impressive for K4 because every vertex in K4 has degree 3. So it's possible that for Kn, you just have 1/n probability of success, and that will still vanish as n goes to infinity. But if you do this for other Kns, you will see that's not the case. Actually, the probability does not vanish, and it converges to something around 1/4. What about other graphs? The line graph of Kn is a strongly regular graph, and you can see that for the first few n's, it drops. But then it immediately goes up and also converges to 1/4. At least from the graph, it looks like so. Any square graph has the same behavior. As the graph gets larger and larger, the average success probability goes to 1/4. And the Paley graph, well, it's not defined for every integer n, but for those that are defined, you can see this is also a limit. Why does this happen? And is it true for this times regular graph with larger diameter? To understand that, we really need to know the eigenprojections of U and what's the product of this eigenprojection with my initial state. So in other words, we need to seriously diagonalize U. And it turns out it's easier to think of U as a product of two matrices. Each of them is an involution. So U is equal to R1, R2, with R1 squared equal to R2 squared equal to the identity. And the R1 is just a permutation matrix that sends arc UV to VU. But R2 is a block diagonal matrix. This is called the coin matrix in physics papers. And each block corresponds to the outgoing arcs of a particular vertex. So what does it do to your arc is that it sends, let's say you start with the arc UV. Then it sends the arc to a linear combination of all the arcs leaving U. So this is sent to, say, V, W, X. And the coefficient will be 2 over the degree of U minus 1 if it stays at the original arc, and 2 over the degree otherwise. And then you multiply this matrix by the arc reversal matrix, you will recover exactly the same matrix we saw in the first slide. Now, this matrix is a reflection, and every reflection is equal to twice the projection minus the identity. For example, this guy is a projection over the all-ones factor because this guy is a reflection about the all-ones factor because J is a projection onto that. So I can write the whole matrix as 2 times some projection minus the identity. And there's a nice expression for n. It's actually the arc tail incidence matrix. So if you bring all these all-ones factor into the same matrix, n is going to look something like 1s, 1s, And the rows are indexed by the arcs, UV, while the columns are indexed by the tails of the arcs. So that's an arc-tail incidence matrix. And the reason why I do this decomposition is because it tells us how to compute the eigenvalues and eigenvectors for you. Turns out you can decompose the state space as a direct sum of invariant subspace of these two reflections. And you can even make all these factors to have dimension most 2. The one-dimensional invariant subspaces are just common eigenvectors on R1 and R2. So there's a nice combinatorial description about these eigenspaces. For the two-dimensional ones, the spectrum of U is completely determined by this matrix. So you transpose the arc-tail incidence matrix, hit it with the arc-by-arc reversal matrix, and then multiply it by n. So you have a short fat matrix multiplied by arc matrix and the transpose. This is tail, arc, arc by arc, arc by tail. And the first two matrices, their product is equal to the head arc incidence matrix. And the head arc incidence matrix times the arc tail incidence matrix is exactly the adjacency matrix of graph. So from the giant matrix U, we recover something that we are familiar with. So here's an example. We have a Pearson graph and its adjacency matrix on the right. It's well known that the Pearson graph has 3 eigenvalues, 3, 1, and -2. So if you look at the normalized adjacency matrix, it has eigenvalues between -1 and 1 with these 3 values. It turns out these eigenvalues determine the real part of the unitary matrix. So you have plus minus 1, which comes from here, and you have 1/3 plus minus the imaginary part that makes this on the unit circle, and you have minus 2/3 that comes from these eigenvalues. Observation holds true in general. We always have 2 real eigenvalues, 1 and -1, appearing in the spectrum, and all the non-real eigenvalues of U will come in this way. Its real part is equal to an eigenvalue of A divided by the degree. And then you can just compute the 2 imaginary parts given the real part. That's what happens if you don't mark any vertex. We get a nice adjacency matrix of the original graph. Now, what if you make a vertex special? Then turns out you are just negating the whole block for that marked vertex. And now instead of reflecting about the all ones factor, this is the reflection about the orthogonal complement. So it will have dimension k-1 if the vertex has degree k. So this matrix is no longer just the arc-tail incidence matrix. You're actually modifying the top part, which becomes, so n tilde looks something like once if the vertices are not marked. So these are unmarked. And you want to put a basis for the column space that you are reflecting about. So the orthogonal complement of 1, which you can take to be the columns of Fourier matrix that's not all one vector. So this will be k-1. And this is a reflection. So the state space can be decomposed into invariant subspaces of dimension 1 and 2. And the spectrum for the dimension 2 subspace is again determined by this. But now you will have an augmented graph because of these extra columns. So what do I mean by that is that on the Pearson graph, we have every vertex is degree 3. So you want to duplicate this vertex, okay, and put the roots of unity on each edge. So let's say omega is the 3rd root of unity, and I can put 1 omega squared for the original vertex, and I can put 1 omega squared and omega for the duplicate. And the adjacency matrix for this augmented weighted graph will determine the eigenvalues of U. So here are the spectrum after normalization, and the plus minus 1 are still there. And you can see each of these real eigenvalues of A tilde will give rise to a pair of conjugate eigenvalues. So here's a summary. We started with big matrix U indexed by the arcs. And if the graph is k-regular on n vertices, this will have size nk by nk. But now after some analysis, we brought that down to a smaller matrix, which has sort of a linear size in n. But we can do even better than this. That the average search probability has this form, and the crucial thing to understand is what is FR times 1, and this FR is the eigenprojection of my transition matrix. There are 3 types of eigenvalues, 1, -1, and non-real ones. Turns out this 1 eigenvalue does not contribute to search because FR times 1 is equal to 0 whenever the graph is 2 connected. And if the eigenvalues are not plus -1, and if the graph has a nice equator partition, for example, when it's distance regular, then FR1 can be lifted from this vector using some incidence matrices. But I won't bother you with the details. The key idea here is you want to hit this with that matrix, characteristic matrix of the vertex deleted subgraph. So this corresponds to all marked vertices, and this corresponds to the duplicates of the marked vertices. And finally, because all the projections FR sum to the identity, the last projection can be computed using I minus all the previous ones. So you get some expression for free. So the problem reduces to what is this vector? And we know E lambda tilde is an eigenprojection of A tilde, the augmented matrix. So it will be a polynomial in A tilde, right? And if we understand each power of A, like how it acts on this vector, then we are done. It turns out whenever X has an equator partition where the first vertex is a singleton cell and its neighbors forms another cell, you have any power of A tilde times this is just the 0 together with the row sum of the mth power of the vertex deleted subgraph. So as a corollary, the only eigenvalues of A tilde that contributes to search will be the eigenvalues of the vertex deleted subgraph. And here's a summary. For U, we have -1 and the non-real eigenvalues that contributes to search. And we can split the average search probability into 2 terms, where the first term comes from the -1 eigenspace, and the other term comes from the non-real eigenvalues. And here V is any neighbor of A. Because we assume X is distance regular, it doesn't matter which one you pick. So this slide shows how you can further reduce the probability to something about X drop A. A tilde, the augmented graph. So we have this 1 omega omega squared and then 1 omega squared omega. This corresponds to A tilde, and recall that we have these many eigenvalues for that matrix, but turns out not all of them contribute to search. So this guy disappears. 0.7 disappears. This is also not there. So we have a much simpler spectrum. And then the thing that contributes to search will just be -1 because the F1 times O1's vector is equal to 0. And then all the other conjugate eigenvalues you find using the vertex deleted subgraph. So the take-home message here is for search, you only care about the vertex deleted subgraph, not the other duplicates. Okay, so we have reduced a problem about the nk by nk matrix to n plus k minus 2 by n plus k minus 2 matrix, and then further down to this vertex deleted subgraph is adjacency matrix. But can we say more about the 2 terms that appear in the average search probabilities? Well, it turns out interlacing will help us a lot by the properties of these ERs. So the first term that comes from the -1 eigenspace, it has this expression where lambda is an eigenvalue of X drop A. And by interlacing, this eigenvalue will lie strictly between minus k and k. So the denominator here is at most 2k. Therefore, we have an upper bound for S1. Moreover, the sum of E lambdas is equal to the identity. So here you are just extracting the first entry of the identity times O1's matrix. And that gives you an upper bound of 1/4 for S1. But we want to divide this by n in the average search probability. So as n increases, this part vanishes. That means we can pretty much forget about this first term when we look at the limit of the probability for a family with growing size. What about the second part? Well, it's a bit more complicated, but we can use a similar idea of interlacing to give a lower bound. And it's actually lower bounded by this quantity over here. So now the question is, if I divide the lower bound by n, does it converge to something that's greater than 0? And there's a nice connection between this second term and the Laplacian matrix of the graph. Because E lambdas are orthogonal to each other for different lambdas, you can write this as a product of two sums, where the first sum is really just Ki minus the adjacency matrix of I. Right? If you expand the spectral decomposition of this guy, you get that thing. And the second term, I will just leave it as is. But now Ki minus the adjacency matrix will be the Laplacian matrix of my original graph with the marked vertex deleted. And this guy commutes with all its eigenprojections. So now you can bring it back into the brackets and ask what is the quantity over here. Because if I know the minimum entry of this, then I can write that as something greater. Let's say the minimum entry is alpha, then they will be greater than or equal to alpha times j. So eventually I will get a lower bound in terms of this sum E lambda j E lambda. And indeed, by induction, you can show that the entries of this vector will increase in distance from A. In particular, it's minimized at the neighbor of A. And the minimum entry of this is equal to n minus 1 over k. So S2 over n is greater than or equal to this number. Okay. And if I can show this converges to 1 as n increases, then I have proved a lower bound for Sn over 2, which is 1/4, and that confirms our intuition from those pictures. We can do some experiments with small graphs. For a complete graph, there are only two eigenprojections, and one of them is orthogonal to O1's vector. So really, this reduces to the O1's matrix. And it converges to 1 as n goes to infinity. It doesn't even involve the variable. And if X is strongly regular, then you have some parameters to play with. But again, it simplifies to something like this. And so when k increases, this term will go to 1. So a summary, for any family of Kn or strongly regular graphs, the average search probability approach to something greater than 1 over 4 as the valency goes to infinity. Now the question is, how about distance regular graphs with larger diameters? I cannot compute E lambda for each lambda when D is large. But I can look at the largest eigenspace. It turns out that will be enough to give me a good lower bound. So here I need to use the tridiagonal matrices and some theory about orthogonal polynomials. If I take a distance regular graph of diameter d with intersection array bi's and ci's, then I can look at the tridiagonal matrix of the quotient graph. But for our purposes, I will look at the reverse one. So you put the AD on the top left corner and A0 on the bottom right corner. Because after all, we are deleting the first vertex of the path, not the last one. Tridiagonal matrix determines the three-term recurrence and is associated with the orthogonal polynomials Qi. So these are the characteristic polynomials of the leading I by I principal matrix of S. And we can define a new polynomial using Qi's and the C's, so that this will become eigenvectors for the corresponding blocks if you evaluate it at the right eigenvalues. Oh, by the way, this reversed diagonal matrix has been studied by Luke and Zhan in 2004. I think they call this dual orthogonal polynomials, and they derive a bunch of nice properties about these QIs. Now, using those polynomials, you can obtain a lower bound on the largest eigenspace. So let lambda be the largest eigenvalue of x drop A, and E lambda be the corresponding eigenprojection. Then for any neighbor of A, you have this quantity. The thing we are interested in S2 is at least n minus 1 over n times this squared. So if lambda gets closer to k as your family grows, then this will get closer and closer to 1. That shows we have a limit of 1 as n goes to infinity. And indeed, by interlacing, we know that not only is lambda less than k when you delete the vertex, but also it's not too far off. So it will be at least k minus some epsilon, and this epsilon depends on k and a. So if I can control this part so that lambda k gets closer and closer, then I'm done. Do I have?
It would be nice if we can finish in 5 minutes.
5, okay. So here's the theorem. For larger diameters, I only care about the largest eigenvalue, and if all the parameters depends on tau, and let's say the valency increases in tau, then we can impose a mild condition on these parameters to ensure the average search probability approach 1/4. And the condition is k to d minus 1 over the number of vertices and over the product of the CIs converges to 0 as tau goes to infinity. And in particular, if you have this ratio goes to 0, then we are good. Captures a lot of graphs with fixed diameters. For example, the Hamming graph with fixed d, the Johnson graphs with fixed d, Grossman graphs with fixed q, and dual polar graphs with fixed e, and many others. That was about families with the fixed diameter. Now you may ask, what if the diameter is increasing? For example, if I take the hypercubes and let q go to infinity, let d go to infinity, then do we still have a non-vanished probability? Turns out it's not. And the reason is, if you think about the initial state, the all-ones factor is a linear combination of the marked vertex and unmarked ones. And it's the unmarked vertices that are to blame, because the returning probability of the marked vertex to itself still converges to something, I think it's at least 1/4, but the other vertices brings this probability down. So I guess I don't have time to describe the details here, but again, for k-regular graphs, if you start with only the outgoing arcs of the marked vertices and look at the average return probability, then without marking, as d increases, this probability vanishes for QD and Johnson 2D D. But with marking, you have a nice plot, and if you plot more graphs, you will see this converges to 1/4 for bipartite distance regular graphs. And if the graph is not bipartite, this probability can even jump higher. It actually gets to somewhere around 3/8. So here's the formula for the lower bound. If x is bipartite, then the average return probability has a very similar form. So if you can control the distance between lambda and k, you can prove this goes to 1/4. And if x is not bipartite, you have again an expression in terms of the dual orthogonal polynomials plus something. I think this is somewhere around 1/8, although I haven't worked out the details yet. So some questions. The number one question is to characterize families of the RGs other than the Johnson graphs and the cubes, on which the average return probability converges to 1/4 or even higher. And especially for which non-bipartite DRGs does this converge to 3/8. And we probably have to explore the properties of the dual orthogonal polynomials and how does that behave if you delete vertices. And question 2 is, will we mark the vertices in the quantum walk? At the graph level, this amounts to deleting these vertices. So, for example, if I mark 2 vertices A and B and look at the state transfer problem. So what is the probability of moving from A to B? Does marking improve this probability? And this problem has been studied in 2017 by Stefanek and Scalbi, and they look at the complete bipartite graph KMM. So it turns out if you mark, then you can boost the probability to somewhere around 1. To further study this on other graphs, we need to know more about the spectrum of X drop A and B. Finally, this is something that I didn't have time to talk about, but the average probabilities of discrete quantum walks, they are actually related to average states of a continuous quantum walk. So back here, I have a formula for the unmarked case. So if M hat is the average mixing matrix for the continuous quantum walk, then the average probability in the discrete quantum walk will be half of this diagonal entry minus something extra. So at the very best, you will get 1/2 probability of return. Can we use the average states on the continuous quantum walks to study the average probability in discrete quantum walks? Again, it will reduce to understanding this on vertex deleted subgraphs. And I think it will be an interesting question to work on. So that's all I want to talk about. Thank you for your attention.
So, is there any question for Harmony?
Yes.
Why are we studying average return probability? Does it imply in particular that there exists a small time at which the return probability is high?
Yeah, actually, that's a question I want to ask that I forgot to include here. I think there should be a connection, but it's not clear like whether it implies the time will be short. I mean, there could exist a time so that the success probability is high, but the time may not be very small compared to N. That's the part I'm not sure.
So in the big picture for spatial search, you want to find a marked vertex in a graph, and you want to argue that classically to find this thing is like takes a long time.
Yeah.
And like exponentially long in number of vertices or something.
Yeah.
Or input size. But quantumly, you can do it quickly in a complete graph, for example, with some model quantum walk. So what does average return probability tell me about the success of such a scheme here? So suppose I have a graph, but I know that the average return probability is high. Then what does it tell me about this game where I want to search the thing quickly?
So you want to know if this high probability tells me what's the time of reaching it, let's say with 1/4.
No, you don't have to say the actual time, but just that just what,
The short answer is I don't know exactly the relation, but the similar technique will actually help us derive an instantaneous probability. So they will translate into a Chebyshev polynomials in time, because you have this k cosine theta thing, and then you have to look at this for every time t. But I think all these orthogonal polynomials will still come in play when you analyze their time.
Yeah, like would it not be slightly more spatial search E to just investigate what happens at time D, where D is the diameter for distance regular graphs, because that is a number that is small, unlike the number of vertices.
Oh, yeah, that's a good question. I haven't thought about fixing the diameter. I mean, you can fix the time that you suspect it will happen, let's say square root of n.
Yeah.
And then do the same analysis. The only difference is you have to include the eigenvalues in the search probability, because now it involves as t increases. But the time is fixed, it's equal to root n. So I think the analysis will be simpler.
Yeah. I mean, we agree that for continuous time, there is some situation where there's exponential time speed up in the glued. Not in search, in the glued trees example, where they find that other vertex, not in the search algorithm. But in discrete time walk, there is no such example. So do you think something could happen with
that's what I was hoping, because without marking, this obvious cannot be, like the search probability is not as good, right? Especially when the diameter is large. But I was hoping if you mark it appropriately, it will boost the search probability at square root of n, or even exponentially faster time.
Any other question for me? So if there's no more topic, let's end again.
Thank you.